We present the MOD, a simple yet effective dictionary learning algorithm that works along the same lines we have just introduced. The MOD was proposed in 2005 by Engan and her co-authors. Here is the architecture of this algorithm. Our examples are shown here as rows of this big matrix. The dictionary is initialized somehow, and now the algorithm starts. First, we update the matrix A. This sparse coding stage is done independently on each example, approximating the representations alpha j. Then we move to update the dictionary while freezing A, and these two steps are iterated. And now let's give more details on each of these steps. Starting with the initialization of D, there are two common ways to choose the starting D. Either by starting from a predefined dictionary, such as a known transform, or by simply taking a random set of the examples. Moving to the sparse coding stage, we consider D as fixed and update the alpha j vectors. Observe that our original formulation suggests that these are n independent pursuit problems, and thus we can apply a pursuit algorithm for each of the examples separately. Naturally, we have the freedom of choosing which pursuit algorithm method to apply. The last of these steps is the dictionary update. MOD chooses a very simple and direct approach. Once A is assumed as known, we can optimize the quadratic expression of the representation error with respect to D. This leads to a simple least squares. Let us now show this in slightly more details. Minimizing this quadratic expression requires nulling its gradient. This gradient is given as the representation error multiplied by A transposed from the right. This equation leads to the update formula, which is simply y times the pseudo-inverse of A transpose. Two small comments are in order here. When A is a very big matrix, this solution can be obtained alternatively by an iterative algorithm of some sort. Also, do not forget that after computing the updated D, we should normalize its columns and absorb the scales back into the rows of A accordingly. When do you stop the algorithm? The most natural condition could either be a fixed number of iterations or an assessment of the representation error. If this error is below what we believe to be the noise level, the algorithm can stop, since this implies that we have the dictionary that fulfills the model conditions, epsilon error and k0 cardinality. Here are two simple tricks that were found to be extremely helpful for MOD and in fact for any other dictionary learning algorithm. These were suggested in a later work by Aaron that will be presented later. Once we have updated the dictionary, we should check whether there are repetitions in it. If two atoms are too similar, we can simply discard of one of them. Similarly, if the dictionary contains a rarely used atom, we could discard of it just the same. Both these cases imply a waste that needs to be taken care of. The question is, what shall we bring in instead? The answer is simple. Identify the signal example that gets the worst treatment, that is giving the largest representation error, and bring it in as an atom. These tricks, while being near trivial, make a huge difference on the success rate of MOD and other dictionary learning algorithms.